Welcome to this SkillPad video resource where we make learning fun. In this video, we are going to look at the immense power encapsulated in the nucleus of an atom. This is the phenomenon of nuclear processes. We live in a world powered by atoms, but most of the energy we use comes from their outer edges. We burn coal, oil, and gas. These processes release the energy stored in the chemical bonds between atoms. But deep within the atom's heart, in the nucleus, lies a far greater source of power. This is the realm of nuclear processes. Nuclear processes involve the nucleus, the tiny, dense core of an atom. The nucleus is composed of protons and neutrons bound together by the strong nuclear force. This force is the strongest in the universe. It overcomes the electrostatic repulsion between the positively charged protons, holding the nucleus together. When we tap into this force, we unleash immense energy. The study of nuclear processes has revolutionized our understanding of the universe. It has given us the power to harness the atom for both beneficial and destructive purposes. From nuclear power plants that light our cities to medical isotopes that diagnose and treat diseases, the applications of nuclear technology are vast. Yet, this power comes with profound responsibility. We must tread carefully, understanding both the benefits and risks of this transformative technology. This journey into the heart of the atom will illuminate the awe-inspiring forces that shape our universe. It will also remind us of the importance of scientific literacy in navigating the complex choices that lie ahead. There are two primary ways to unlock the energy within the atom. These are the processes known as nuclear fission and fusion. Fission is the process of splitting a heavy nucleus, such as uranium or plutonium, into lighter nuclei. Imagine splitting a log of wood. You get two smaller pieces, and a bit of energy is released as heat and light. Fission is similar, but the energy released is millions of times greater. Fusion, on the other hand, is the process of combining light nuclei such as isotopes of hydrogen into a heavier nucleus. Think of combining droplets of water. They merge into a larger drop, releasing a tiny amount of energy. Fusion in stars combines hydrogen nuclei into helium, releasing the energy that powers the sun. Both fission and fusion involve a change in the binding energy of the nuclei. Binding energy is the energy that holds the nucleus together. When a heavy nucleus fissions, the binding energy of the daughter nuclei is greater than that of the parent nucleus. This difference in energy is released, primarily as kinetic energy of the fission products and neutrons. Similarly, when light nuclei fuse, the binding energy of the product nucleus is greater than the combined binding energy of the reactants. The difference in energy is released, mostly as kinetic energy of the products, and in the form of high-energy photons, such as gamma rays. These processes, fission and fusion, are the cornerstones of nuclear energy and the source of the sun's power. However, not all atoms are stable. Some nuclei are like restless dancers, constantly shifting and changing. This is the essence of radioactive decay. Radioactive decay is the spontaneous process by which an unstable atomic nucleus emits particles or energy to become more stable. Imagine a popcorn kernel. You can't predict exactly when it will pop, but you know it will eventually. Radioactive decay is similar. We can't predict when a specific atom will decay, but we can determine the probability of decay over time. This probability is expressed by a concept called half-life. Half-life is the time it takes for half of a given amount of a radioactive substance to decay. Think of it like this. You have a bag of 100 pennies. Every minute you flip each penny. If it lands on heads, it decays and you remove it from the bag. After one half-life, you would expect to have about 50 pennies left. After another half-life, you would have about 25, and so on. This concept of half-life is crucial for understanding the long-term effects of radioactive materials. It helps us determine how long it takes for radioactive waste to decay to safe levels, and is essential in fields like archaeology and geology for dating ancient artifacts and rocks. Radioactive decay produces several types of radiation, each with unique properties and behaviors. The most common types are alpha, beta, and gamma radiation. These are like three different instruments in an orchestra, each producing a distinct sound. Let's tune in to their individual melodies. Alpha radiation consists of alpha particles, which are essentially helium nuclei, 2 protons and 2 neutrons. Imagine a tiny cannonball being fired from the nucleus. Alpha particles are relatively massive and carry a positive charge. They interact strongly with matter, meaning they can't penetrate very far through materials. A sheet of paper or a few centimeters of air can stop them. Beta radiation, on the other hand, consists of beta particles, which are high-energy electrons or positrons. Think of these as nimble, fast-moving electrons. Beta particles are much lighter than alpha particles and carry a negative or positive charge. They can penetrate further through materials than alpha particles, requiring a few millimeters of aluminum or a similar material to stop them. Finally, gamma radiation is not a particle, but a high-energy electromagnetic wave. Picture a ripple of pure energy, like a wave of light, but with much higher energy. Gamma rays have no mass and no charge. They are highly penetrating and require thick layers of lead or concrete to attenuate their intensity. These different types of radiation interact with electric and magnetic fields in predictable ways. Alpha and beta particles being charged will be deflected by these fields. Gamma rays having no charge will pass through these fields undeflected. This interaction with fields allows us to detect and manipulate these radiations, which is vital in various applications, from medical imaging to nuclear research. The discovery of nuclear processes has been a game changer for humanity. It's like discovering fire. We can use it to cook our food and warm our homes, but it can also burn and destroy. Nuclear technology offers both immense promise and potential peril. On the one hand, we've harnessed the power of the atom for peaceful purposes. Nuclear power plants provide a significant portion of the world's electricity. Medical isotopes are used in countless diagnostic procedures and treatments, saving and improving lives every day. In agriculture, radioactive isotopes are used as tracers to study plant metabolism and develop more efficient fertilizers. In industry, they are used for gauging the thickness of materials and detecting flaws in welds. Archaeologists use carbon dating based on the decay of carbon-14 to determine the age of ancient artifacts. Geologists use radioactive dating techniques to determine the age of rocks and study geological processes. The applications of nuclear technology are far-reaching, impacting our lives in numerous positive ways. Nuclear power, in particular, presents a compelling dilemma. It's a carbon-free source of energy which is crucial in our fight against climate change. Nuclear power plants don't emit greenhouse gases during operation, making them a potentially attractive alternative to fossil fuels. However, nuclear power also carries significant risks. Accidents at nuclear power plants, while rare, can have devastating consequences, as seen in Chernobyl and Fukushima. The disposal of nuclear waste, which remains radioactive for thousands of years, is a complex and unresolved issue. The potential for nuclear proliferation, where nuclear technology is used to develop weapons, is a constant concern. The threat of nuclear terrorism adds another layer of complexity to this already challenging issue. The decision of whether or not to rely on nuclear power is a complex one, with no easy answers. It requires careful consideration of the scientific, economic, environmental, and ethical implications. Open and informed public discourse is essential for navigating this complex landscape. As we conclude, it's imperative to appreciate that we live in a radioactive world. From the potassium-40 in our bodies to the cosmic rays bombarding us from space, radioactivity is a natural part of our environment. Understanding the nature of radioactivity and its effects is crucial for making informed decisions about our health and safety. Exposure to high levels of radiation can damage cells and DNA, leading to an increased risk of cancer and other health problems. It's essential to minimize unnecessary exposure to radiation, especially from medical procedures and other artificial sources. As we continue to explore the atom and harness its power, we must proceed with caution and a deep sense of responsibility. The future of nuclear technology depends on our ability to balance the pursuit of knowledge and innovation with a commitment to safety, security, and sustainability. The journey into the atom has revealed a universe of incredible power and complexity. It is a journey that continues to this day, challenging us to think deeply about our place in the cosmos and our responsibility for the future of our planet. Thank you for using this SkillPad video resource. We hope it was resourceful. Come with us as we explore the world of science for your learning pleasure. We hope to see you again soon.